Intermediate Algebra Section 1.6. We now develop rules for manipulating exponents and determine what zero and negative integers will mean as exponents. And let's lay down some of these rules here. For the product rule, when you have common bases multiplied together, you will add the exponential powers together. The quotient rule, provided that m is greater than n, is such that if you have common bases being divided, you can have an equivalent value by taking the common base and subtracting the exponents. We also have something called the zero exponent, and this is for any non-zero real number a raised to the 0 power. It is equal to 1. The expression 0 to the 0 power is undefined, and we'll see some examples shortly on how these rules actually work. We also have something called integer exponents for any non-zero real number a and any integer n. If you have a to the negative n, it is equal to 1 over a to the n power. Furthermore, if you have a negative exponent in the denominator, it's equivalent to that base raised to the positive. A power rule is from raising a term with an exponent to a power is equivalent to multiplying those exponents together. Another rule that we have is raising a product to a power, which is describing essentially what we have. We have a product, these two things multiplied together, raised to a power, means that each factor will be raised to that power. So a will be to the n and b will be to the n. And if we have a quotient raised to a power, well, a quotient is the result of a division. If it's raised to a power, that means each of the components, the numerator and the denominator, are raised to that power. So let's take a look at simplifying some expressions using those properties that we just went through. They're asking us here to simplify x to the third times x to the fifth. We can use that product rule, since we have common bases multiplied together, and add the exponents, which is equivalent to x to the 8th power. If at some point you're not convinced that this is correct, we can always take the time, translate this into the expanded form. X to the third is x times x times x. X to the fifth is 5x's multiplied together, and then simplify from there. If we have the parentheses determine our, scratch that, the parentheses have no effect, so we have multiplication of 8x's together, which we would write as x to the 8th power. The next problem, we have common bases multiplied together, just like the previous one. Since we have common bases, we can add the exponents together for a shortcut, which gives us 9 to the 15th power. Because this is an incredibly large number, we'll leave it written in this form. In this next problem, we have multiplication within the parentheses and parentheses next to one another, which is multiplication, and again multiplication within the second set. Using commutative property then, and ignoring the parentheses since it's all multiplication, rearranging the numbers, the order, that's commutative property, we can simplify this expression. I've essentially just turned the order of these two around, putting the -3 in front of the x to the 7th. so that I'm multiplying the integers can be simplified. A positive times a negative is a negative. 2 times 3 is 6. And common bases, we will add the exponential powers for a final answer of negative 6x to the 11th power. Similar to this one, whether you physically rewrite it using commutative order, putting similar terms together, or mentally, since inside here this is all multiplication, parenthesis next to parentheses multiplication, and again multiplication, rearranging using commutative property that allows us to multiply in any order. We've got our like terms together. Negative times a positive is a negative. 20 times 6 is 120. We have common bases multiplied together. This second x doesn't have an exponent, but it's understood to have an exponent of 1. Common bases, add the exponents, would be x to the 3 or third power. Similarly, we have y to the third times y, which would be y to the first. Common bases, add the exponents. 3 plus 1 is going to have our y to the fourth power. Now, if you have a question about x to the first, for example, we had x squared times x, and I said it was to the first power. Write this out in expanded form to verify that. X to the second is x times x. We're timesing it by an x. If we had 3 x's multiplied together, we would write it as x to the third power. So the final answer to this problem is here, because similarly, the y's would work the same way as the x's. And when there isn't an exponential power, we have to use the fact that it is an implied 1. Let's look at a couple more examples illustrating some of those properties that we outlined. We have multiplication within the parentheses and parentheses together. So a quick sort of like terms together. Putting the integers and the x's, we have 2 times 5 is 10. Common bases, add the exponents. Now this second x doesn't have an exponent, which is giving us the implication of a 1. Common bases, add our exponents. 0 plus 1 leaves an x to the first power, which we would write as simply 10x then. And how does that work? By definition, the 0 exponent in our list, 0, anytime 0 is your exponential power, it's equivalent to 1. And that appears to be the case. X to the 0, we verified it by common bases adding our exponent. We ended up with just the x, treating this as though it were a 1 times x, giving us an x. Here we have a quotient, common bases. The quotient rule says then to subtract the exponent. So we have a 12 minus 3 is leaving us with an x to the 9th power. If that property, again, is one that you're not sure of, write them out in expanded form. So we have 12 x's. I think I have 12. 3 x's. Let me verify. 2, 4, 6, 8, 10, 12. And x to the third would be 3 x's. Anytime we have a common factor over itself, they cancel out equal to 1. So I can cancel out 3 sets of x's. And what's left is 1, 2, 3, 4, 5, 6, 7, 8, 9 x's, or x to the 9th power. Takes a little longer in expanded form. The exponential properties are there for shortcuts, and with enough use, they become second nature. In this last example here, we can break this product in the numerator and the denominator into components of similar terms in the numerator over similar term in the denominator to simplify this. And at some point you may be doing this mentally, but just to illustrate what's going on, we have a Positive divided by negative is a negative 6. Common bases in a quotient means we will subtract the exponents when a division is occurring. Same thing here. N to the 5th minus the exponential power in the denominator of 2. Simplifying, we have a negative 6, m to the 2nd, n to the 3rd power.